Okay. Um, so today it's the last day, um, and I wanted to talk about combinatorial consequences of choiceless cardinals. Particularly in cardinal arithmetic, and particularly the ones that are related to the periodicity phenomena for choiceless cardinals. So remember, we had this theorem from a few days ago that if alpha is an ordinal and j from v alpha to v alpha is elementary, j is definable over v alpha if and only if alpha is odd. And also, we had the theorem, or the fact, that if j from v to v is elementary, then the kappa omega of j is a rank Berkeley cardinal, which in particular means for all alpha greater than or equal to kappa omega of j, there is an elementary embedding from v alpha to v alpha. So we have this periodicity property of v alphas that admit elementary embeddings to themselves, and eventually it takes hold for all of the v alphas. But the sort of defect in this result, it's not exactly a defect, but it's only giving us a periodicity property of the very elementary embeddings we're studying. It's not telling you something, it's telling you about large cardinal properties. It's not telling you about the sort of properties that Cantor would have studied. So it's a periodicity feature of the universe of sets under these large cardinal properties, but it's sort of internal to the theory. And I want to talk about consequences of choiceless cardinals that have these periodicity features, but the features that we're looking at now, I want them to be expressible without reference to things like elementary embeddings and definability. So the basic concept that we're looking at is this ordering. So under the axiom of choice, the existence of an injection from one set into another, which is typically denoted by x is less than y if x injects into y. It's equivalent to the existence of a surjective function from y to x well, okay, basically, and unless x is empty. If x is empty, then the only thing that will surject onto it is the empty set, because you can't have a function on a non-empty set with an empty range. Okay, so so this is the less than or equal to star relation on sets. Sometimes, well, it's usually easier to write this, which typically doesn't cause any ambiguity. Here it might, because there are lots of different things that are denoted this way. Okay, so these two relations can be different if the axiom of choice is not assumed. So the two ordinal invariants of sets that are studied in this choiceless context are one, the Hartog's number of X, which is the supremum of all ordinals alpha, such that there is an injection from alpha to X, and the Lindenbaum number of X, which is just the supremum of all ordinals alpha, such that there is a surjection from X onto alpha. So in the context of AC, we have that aleph of X is equal to the successor of the cardinality of X, and that's also equal to aleph star of X. But in the context where choice isn't assumed, these things can be very different. So for example, under the axiom of determinacy, which we've talked about a little bit, we have that the aleph of R, the Hartog's number of R, this is the least ordinal eta, such that there is no eta sequence of distinct real numbers. And if you think about it, it's very hard. I mean, this is just true in general, but it's very hard to define any uncountable sequence of real numbers. In fact, under AD, there is none. So there's no omega-1 sequence of distinct real numbers. It's an easy exercise to show that no omega-1 sequence of real numbers can be of distinct real numbers can be continuous, for example. So this has to be sort of pathological, and in fact, if there's an omega-1 sequence of real numbers, there has to be a non-measurable set. That's, I can't remember who proved that theorem, maybe Shalah. It's not that obvious because there are omega-1 sequences of distinct real numbers, say assuming CH, that enumerate a measurable set, for example, all of the reals. So it's it takes a little bit of work. Okay, so, but it actually takes more than a little work. Okay, so let's see. So I want to study these theta alpha. So on the other hand, under AD, the aleph star of R is this cardinal I was calling theta. It's just the supremum of all ordinals that are the surjective image of R. And AD implies that theta is a strong limit cardinal. Which just means that theta is not the surjective image of P of eta for any eta less than theta. So in particular, theta can't be a successor cardinal. So I want to talk about these generalized thetas. So for each alpha, let theta alpha be equal to the supremum of all ordinals eta, such that for some beta less than alpha, eta is the surjective image of V beta. So another way to write this is that theta alpha is equal to either the supremum of all the theta betas for beta less than alpha, if alpha is a limit ordinal, or it's equal to this Lindenbaum number of V alpha minus 1, if alpha is a successor. Okay. And the periodicity theorem that I wanted to prove, well, I won't really prove it, but I'll give some of the ideas, is that if you look at a rank Berkeley cardinal, so for example, as I showed, kappa omega of J for J, an elementary embedding from V to V, and you take kappa greater than or equal to lambda, it's rank reflecting. So these were the ordinals that I used last time to prove this well-ordered collection lemma. But for example, you could just assume that kappa is any ordinal such that V kappa is a sigma 2 elementary substructure of V. Then, and so now the periodic part, if epsilon greater than or equal to kappa is even, so this was supposed to say and, then 1 theta sub epsilon is a strong limit cardinal. So that means just that for eta less than theta epsilon is not a surjective image of the power set of eta. And 2, theta epsilon plus 1 is not a strong limit cardinal because it is the surjective image of the power set of theta eta. Okay. So I'm not really going to talk about this part of the theorem. How do you construct a surjection from the power set of theta epsilon onto theta epsilon plus 1? The construction, it uses similar ideas to what will be done in 1, actually. But of course, it gives you the opposite result. So what's the idea behind this theorem? It will ultimately trace back to the periodicity theorem that Schlutzenberg and I proved, the one about the definability of elementary embeddings. So what it will actually use is this theorem from one of the exercises. So what I'll need is this fact. So let's work with elementary embeddings from V to V just to make it a little easier to state things. So maybe I'll be working in this context instead of just with a rank Berkeley. So if J is an elementary embedding from V to V, and J fixes the even ordinal epsilon, then J restricted to theta epsilon is not definable over V from parameters in the range of J union V epsilon. Okay, so this is a version of the periodicity, the undefinability of elementary embeddings from an even rank to itself. Okay, and so how will this help? Well, I want to show, so fix an ordinal eta less than epsilon. We want to show that the power set of eta does not surject onto, less than theta epsilon. Does not surject onto theta epsilon. So for this is gonna require another fact, which is also from the exercises. If J, let's stay with J from V to V, and X surjects onto Y, or basically Y surjects onto X, and J image Y is definable over V from parameters in the range of J, along with whatever other parameter you want. Then so is J image of X. So this form of definability of these fragments of the embedding J, or the image of J on some set, is downwards closed under this relation. And that's going to be the key. So Y, if you didn't do the exercise, well, let F be a surjection from Y to X, and notice that J image of X is actually just equal to set of J of F of little y's for, well, say J of F of u's for U in J image of Y. So that allows us to define J image X from J image Y and some point in the range of J, namely J of F. So it's a pretty simple fact, but it will lead to the theorem the following way. But it reduces everything to showing that in this context, where kappa is this rank reflecting cardinal, we want to show that J restricted to the power set of eta is actually definable. So remember, eta was less than theta epsilon. I want to show it's definable from parameters in in V epsilon. And then it follows that the power set of eta cannot surject onto theta epsilon, because otherwise you get that J image theta epsilon is definable from parameters in J, the range of J along with V epsilon by the second fact. So there's something going on here that might be a little confusing. I mean, J image theta epsilon and J restricted to theta epsilon, they're essentially the same object. And this is true whenever you have a transitive set. So for example, the power set of the ordinal eta is a transitive set. And so J restricted P of eta is essentially the same thing as J image P of eta. That's not true for non-transitive sets. So this fact, if you want to state it in this simple way, you have to talk about J image x's. If I just assume that x and y are transitive, then I could have written J restricted to y, J restricted to x. Okay, so I only care about the case when x and y are transitive anyway, so I only have to care about the actual function J, but it's really a small detail here. But the point is, since we'll be able to define this map from small parameters, and we know that this map is not definable from small parameters, relative to parameters in the range of J, which we always allow, follows that there cannot be a surjection from this set onto this. Okay, but the real challenge is to define one thing I want to say though, we might as well we can reduce to the case where epsilon, well, to the successor case, the case where epsilon is a limit ordinal is trivial. I mean, okay, there's something to think about, that theta epsilon is, if epsilon is a limit, is always a strong limit cardinal. In ZF, and theta epsilon plus 1 is equal to theta epsilon plus provably in ZF. Okay, if epsilon is a limit. So we're really interested in the case where epsilon's not a limit, or in other words, let's consider epsilon plus 2. So we might as well be looking at epsilon plus 2. I just don't want to introduce a new name for epsilon. So we could be looking at the case where epsilon is equal to epsilon bar plus 2. And then for ease of notation, I'm just going to talk about epsilon plus 2. Okay. Is that confusing to anyone? I know you're graduate students. You can handle me changing my notation. It's okay. Okay. So we have So we have eta, it's less than theta epsilon plus 2, and we're trying to show that the power set of eta doesn't surject onto theta epsilon plus 2. And we wanted to do that by defining J restricted to the power set of eta from parameters in the range of J union V epsilon plus 2. But what we'll actually need is just J restricted to V epsilon. And of course, we'll use J on V epsilon plus 1. Those J on V epsilon, remember from the periodicity theorem, recovers J on V epsilon plus 1. So this is the key thing to use. So note that for any ordinal, gamma below theta epsilon plus 2, we can get J restricted to gamma, or J image gamma is definable from J on V epsilon plus 1. And this is just the fact I just stated about sets that surject onto each other. So this is just because by the definition of theta epsilon plus 2, we have that gamma is the surjective image of V epsilon plus 1. Right, theta epsilon plus 2 was just equal to the Lindenbaum number of V epsilon plus 1. So by the fact tells you that J restricted to gamma is definable from parameters in the range of J plus J on V epsilon plus 1. Okay, but that's not good enough. We want J on the power set of gamma. And so it feels a little circular. Like we would be able to get J on the power set of gamma if we knew how to surject V epsilon plus 1 onto the power set of gamma. But the whole thing we're trying to do right now is show that the power set of gamma doesn't surject onto theta epsilon plus 2. But to do that, of course, if we knew that V epsilon plus 1 surjected onto the power set of gamma, then we would know that the power set of gamma can't surject onto theta epsilon plus 2, because the whole point of theta epsilon plus 2 is it's not the surjective image of V epsilon plus 1. So, so this kind of very simple method for showing that this is definable can't work. We can't do it just by surjecting V epsilon plus 1 onto the power set of gamma. I mean, well, it would be great if we could do that, but it's actually an open question. Does V epsilon plus 1 surject onto the power of gamma in this case? If we could do that, we'd be very much done. But that's not the approach I'll take. I want to define this, or J on the power set of eta is, I guess, the ordinal I started with, in some other way, because that's all I know how to do. So the way to do it is to view J restricted to the power set of eta as a sequence of ultrafilters. So this is somewhat similar to one of the constructions on the first exercises. How do you get it's the generalized ultra powers that allow you to represent strong cardinals as a form of ultra power embeddings. So otherwise known as extenders, but you don't even have to know about anything about extenders to understand this part of the proof. So how do you view J on the power set of eta as a sequence of ultrafilters, and why does that help? I'll tell you the answer to both of these questions. So for each alpha less than J of eta, well, I guess I assume J of eta, I can assume J of eta is equal to eta. Whatever. Let E sub alpha be the set of all A contained in eta, such that alpha goes into J of A. Okay, so E alpha is the ultrafilter derived from J using the ordinal alpha. It's a countably complete ultrafilter on eta. It's actually it's a kappa complete ultrafilter. No, not kappa is taken, I guess. Remember, kappas are whatever rank reflecting cardinal. So this is a rho complete ultrafilter on eta, where rho is equal to the critical point of our embedding J from V to V. Okay, so we have this J of eta length sequence of ultrafilters, E alpha, alpha less than J of eta, and I claim this is essentially the same thing as J restricted to the power set of eta. So J on the power set of eta can be reorganized as a sequence of ultrafilters of length J of eta. So namely, if you want to compute what is J of some subset of eta, well, J of A is just equal to all of the alpha less than J of eta, such that A is in E sub alpha. Just by definition, right? Because we put A into E sub alpha if and only if alpha went into J of A. So it's really just a reorganization of J on eta. And of course, E sub alpha is just defined from J restricted to the power set of eta, because it's just the set of A such that alpha is in J restricted to the power set of eta applied to A. So the two objects are the same thing, but somehow it's better to think of the sequence of ultrafilters in this case. And the reason is that it turns out that in this context, there is a lot you can say about the the complete ultrafilters on eta. So let beta so let beta WF of eta, or well, sure, whatever, be the set of all ultrafilters U on eta, such that the ultra power of the ordinals by U is well-founded. So the issue here is we're working in ZF, So in ZFC, or even just ZF plus DC, this is equivalent to being omega 1 complete. So closed under countable intersections. But in the context of ZF alone, that is not an equivalence. So so we have to work with this set in particular, or else things don't work as nicely. Okay, so if we it would suffice to know that the, the well-founded ultrafilters on eta are the surjective image of V epsilon plus 1. So why is that? If that were the case, then also, so we're trying to show that we need to show that this sequence of ultrafilters, E alpha, alpha less than J of eta, which is contained, turns out, in the well-founded ultrafilters on eta. It's pretty easy to see, actually, that these are all well-founded because they can be factored into this embedding from V to V. So every component ultrafilter of an embedding from V to V has to be a well-founded ultrafilter, not just countably complete, but in fact well-founded. Okay, so we need that this sequence is definable from J restricted to V epsilon plus 1. So this is just, but this sequence, it's a sequence of elements of this, so it can be reconstrued as a subset of the product of J of eta times the well-founded ultrafilters on eta, which is again the surjective image of V epsilon plus 1, since each component is the surjective image of V epsilon plus 1, and the product of V epsilon plus 1 is below. You showed that there's a pairing function on V. I put it on the homework that there's a pairing function on V epsilon plus 1. But not talking about pairing functions today. Okay, so, so we have that we're just trying to define some subset of this from this guy and parameters in the range of J. The point though is that every subset of V epsilon plus 1 is definable from this and parameters in the range of J. And so if you have a surjection from this onto here, that follows that every subset of this guy is definable from parameters from this and parameters in the range of J. So one more page of this reduction to the question of the cardinality of ultrafilters, and then move on. So what's the point here? Note that if A is contained in V epsilon plus 1, then A is definable from J of A and J restricted to V epsilon plus 1, because A is just equal to J restricted to V epsilon plus 1 inverse image of J of A. And so any subset, given any subset well, given any set X, which is less than or equal to V epsilon plus 1, if we have, if you have a set B contained in X, then B will be definable from J of B, J restricted to V epsilon plus 1, and J of some surjection from V epsilon plus 1 onto X. Well, I guess the main point is this fact is showing that if you have J restricted to some set like V epsilon plus 1 or whatever set you want, X, then you can define any subset of X from point in the range of J and J on X. And we can get, so J on, for example, this set, because we know J on V epsilon plus 1 and we have the surjection. So we can use this old fact that I wrote down a long time ago. And so anyway, it just follows that every subset of this is definable from this and parameters in the range of J. And the sequence of ultrafilters we're interested in is a subset of this, or its graph is a subset of this. And so we'd be done if we knew this fact. So yeah, I'm going to focus for basically the rest of the talk on the analysis of the well-founded ultrafilters on eta. So if you have any questions about the reduction of the problem of showing theta epsilon plus 2 strong limit reduces to this, please tell me now.
So could you please say more about this? This proof?
About this reduction?
Yes.
Okay. So yeah, so the point was to show theta epsilon plus 2 is a strong limit. It sufficed to show that we could define J restricted to the power of eta from parameters in the range of J plus J restricted to V epsilon plus 1. So are you okay with that?
Yes. Yes.
Okay, then to do that, we just needed to show that this sequence of ultrafilters E alpha for alpha less than J of eta. So we needed that this sequence of ultrafilters E alpha for alpha less than J of eta is definable from parameters in the range of J union J on V epsilon plus 1. Just because this sequence of ultrafilters is the same thing as this, basically. They're interdefinable. Okay, so that reduces it all to a question about a sequence of well-founded ultrafilters. So to get that this is definable from parameters in the range of J union whatever, suffices to know that in fact, every subset of J of eta times V epsilon, sorry, times, times the well-founded ultrafilters on eta is definable. I hate saying this over and over, from parameters in range of J union J on V epsilon plus 1. That okay?
Yes.
So then, yeah, so the last step, I made it more confusing than I should have. So if you know fact, if X is less than or equal to V epsilon plus 1, then every subset of X is definable from parameters in this set or class. I'm not going to write this down again because actually it's more saying it that is killing me because it's so hard to say anything right now. Okay, so why is that true? Well, in general, this is an observation due to Solove in the context of supercompact cardinals. Every subset of X is certainly definable from J image X and parameters in the range of J, because it's just if you have a subset A X, A is just equal to J inverse image J of A. But I already said that if since if X is less than or equal to V epsilon plus 1, then J image of X is going to be definable from J restricted to V epsilon plus 1 and parameters in the range of J. Okay, finally, so putting that together, so that it follows that if X is less than or equal to star V epsilon plus 1, then every subset of X is definable from parameters in the range of J union J on V epsilon plus 1. Okay, so if we knew that the well-founded ultrafilters on eta had, were the surjective image of V epsilon plus 1, then also J of eta times this would be the surjective image of V epsilon plus 1. And so every subset of this would be definable from parameters in here. And in particular, the sequence of E alphas would be definable in the way we want it to. Does that help?
Yeah, thanks.
Of course. Yeah, I'm sorry I made it a little bit unnecessarily confusing the first time. Okay, so let's see. So I want to show that this set is the surjective image of V epsilon plus 1. But what I'll talk about instead is, remember, we have this rank reflecting cardinal. And the really substantive part of this is showing that the kappa complete ultrafilters on eta, which, as if you remember from last time, that's a well orderable set. So we can talk about its cardinality as an ordinal, and the key is to show that this has cardinality less than theta epsilon plus 2. So the theorem, which I'll write down, if eta is less than theta epsilon plus 2, then the set of kappa complete ultrafilters on eta has cardinality less than theta epsilon plus 2. So since this is a well orderable set, this is actually equivalent to saying that beta kappa of eta is the surjective image of V epsilon plus 1. Any well orderable set that's the surjective image of V epsilon plus 1 has cardinality less than theta epsilon plus 2, and conversely, any ordinal below theta epsilon plus 2 is by definition the surjective image of V epsilon plus 1. So so this is slightly weaker than this fact, but it turns out that this is really the key to the whole thing, and it's going to be really important in the proof that this is a well orderable set. I mean, that's really the only thing I'll need to show this. So I don't want to talk too much about how you get to this from this, because it's a little bit sort of routine if you know enough about ultrafilters, but it's not routine if you don't, and I don't want to say too much about it. But the point is that you can actually represent any ultrafilter in here as a pair of ultrafilters. Let's call it D and U star, where U star is actually kappa complete ultrafilter on eta, and D is actually just an ultrafilter on kappa. Or even on an ordinal less than kappa. And so there just aren't. So this set we know is small, and this set, it's going to be the surjective image of something much less V epsilon plus 1. For example, V kappa, it'll be the surjective image of V kappa. So putting those two things together, we get this full fact. But I'm not going to talk too much about that. So this is what I'll talk about. And so since we're just about to get into the theory of ultrafilters under embeddings from V to V, why don't we take the break now for 30 minutes until 30 after the hour, and then I'll start talking about that. Okay.
Okay.
Okay, I think we have another minute of the break, so I'll wait until 8:30.
Okay. Nope.
But
Yeah, no problem.
all right, so remember where we were, just trying to prove this fact about the cardinality of the kappa complete ultrafilters on an ordinal, just a bound. And one way to think about this is it's another inaccessibility property of this ordinal theta. We're trying to prove that theta is a limit cardinal a strong limit cardinal. And this is another way, I mean, in ZFC, it's another property that strong limit cardinals have that we're going to prove of theta. And I've already shown you how proving that theta is a strong limit cardinal will reduce to that. I just want to note that in L of R, it's actually not true that theta is a strong limit cardinal in this sense. So remember the ordinal theta of L of R, which is just the theta omega plus 2 as computed in L of R. So the supremum of the ordinals that are the surjective image of R it is not a strong limit in the ultrafilter sense. In fact, there are arbitrarily large delta less than theta of L of R, such that the set of normal ultrafilters, or let's just say delta complete ultrafilters on delta, has cardinality equal to theta of L of R in L of R. So this situation is a little different from the basic determinacy situation, but actually it is a theorem of Kekris that assuming the determinacy of all real games, for every eta less than theta omega plus 2, which is sometimes called theta, the cardinality of the set of countably complete ultrafilters on eta is less than theta. So the theorem we're proving is actually an analog of a consequence of real determinacy, which makes sense because we have, we're assuming a rank Berkeley, or what I was working with is just a J from V to V. So we should have analogs of ADR instead of just what's going on in the V is equal to L of R case. Okay, so anyway, the motivation for the techniques that I'm going to use to try to solve this problem of bounding the size of the set of kappa complete ultrafilters on eta comes sort of in a roundabout way from my dissertation. So the dissertation is about a combinatorial principle, a set theoretic principle called the ultra power axiom. The motivation for this axiom comes from the theory of canonical inner models that I talked about a little bit on Tuesday, maybe. So in that theory, you're trying to build canonical structures that satisfy ZFC plus large cardinal axioms. And one way in which the structures you build are canonical is that if you take any two of them, it's possible to find structures N0 and N1 into which they both elementary embed, such that either N0 is equal to N1, or N0 is in N1, or N1 is in N0. So there's a trichotomy here, but it allows you to compare these two structures. So M0 is like less than M1. If this one holds, it's equivalent if this holds, and it's the other way if the other way holds. Okay, what the ultra power axiom tries to do is give an abstract but precise principle that has some of the power of this canonicity property of the models that come from intermodal theory. So this is called the comparison lemma, by the way. The ultra power axiom just says that if you take the universe of sets V and you take any ultra powers of V, so say you take the ultra power of V by two countably complete ultra filters. So this is going to give you two inner models of V, and in the context we're interested in, there are inner models that satisfy ZFC, since these are elementary embeddings. The ultra power axiom says that in this case, there have to exist further ultra power embeddings of these two models into a common structure, also a transitive inner model of ZFC. So what W0 and W1 are supposed to be countably complete ultra filters in M0 and M1. So the ultra power axiom says that you can find these things and the diagram commutes. So for all U0, U1 countably complete ultra filters, there exist W0 in the ultra power of U0 and W1 in the ultra power of M1, which look like countably complete ultra filters in the models where they're selected, such that the ultra power of M0 by U0 is equal to the ultra power M1 by U1, and the diagram commutes. So that means JW0 composed with J U0 is equal to JW1 composed with JU1. Okay, the two embeddings are the same into N. So it turns out that this principle is quite useful for studying ultrafilters, just the structure of ultrafilters. So for example, one can prove using it that the least strongly compact cardinal is super compact. The GCH, so this is under UA. GCH holds above the least super compact or strongly compact, since they're the same. If there's a strongly compact, then the Hod conjecture holds. So these are all theorems of ZFC plus UA. So what's going on is the strongly compact gives you all the ultrafilters, and UA gives you all the structure on the ultrafilters. And using those two things together, you can find a lot of structure on sets. So for instance, proving things like GCH. So I want to talk a little bit more about how this works, because it's related. Well, first of all, it makes it look like, okay, the ultra power axiom couldn't be farther from the situation we're in right now, the choiceless cardinals. But actually, that's not the case. I should say a little bit more about the metamathematical situation with the ultra power axiom. The ultra power axiom is not provable in ZFC. Okay. And in fact, if you have no measurable cardinals, then the ultra power axiom is true because there are no ultra powers to take. So it's vacuously true. But if you have a measurable cardinal, the only way that's known to get a model of UA with a measurable cardinal is to start with a canonical model with a measurable cardinal. So UA really forces you into being in some kind of canonical model, as far as we know. There's no way to produce models of UA without going through canonical models of set theory. And all the canonical models do satisfy the ultra power axiom. Makes sense to ask that because UA is just a first order principle about ultrafilters. It's not like this comparison lemma, which was a sort of vague principle. I didn't really define it completely. Okay, so what does this have to do with choiceless cardinals? Or, I mean, even all this stuff, none of it can even be formulated in the context without choice, because you don't even have that these ultra powers are elementary embeddings without assuming the axiom of choice. So it doesn't make all that much sense to talk about taking ultra powers within these models, because they're not even models of ZFC or even models of ZF. They're not even extensional structures. So that's makes it a little weird to think about in this context. So there's a combinatorial characterization of the ultra power axiom that doesn't talk about ultra powers at all. It just talks about a certain order on ultrafilters that was defined originally by Kettinen. So how do you define it? It's called the Kettinen order. So suppose you have suppose delta is an ordinal, and you have ultrafilters U and W on delta, whose such that the ultra power of the ordinals by U and W is well founded. Okay, then I guess it doesn't matter that they're on the same ordinal. So you could have U is in beta well founded of delta 0, and U1. No, let's not do it that way. There aren't enough letters for ordinals. Okay, then U is less than W in the Kettinen order if there are ultrafilters, say U alpha, for alpha less than delta 1, such that, well, first we want that U is a sort of limit of these ultrafilters under W. So U is the collection of all the subsets of delta 0, such that for W almost every alpha less than delta 1, A is in U alpha. Okay, so that's one thing, but okay, one way to do this would just be to take U alpha equal to U for all alpha. So this doesn't have any substance on its own. But the point is, we also demand that these ultrafilters are not too big. In other words, that for almost all alpha less than delta 1, U alpha actually concentrates on alpha. So if alpha is in U alpha, then U alpha is essentially an ultrafilter on alpha. And you could reformulate this so that we say U alpha is literally an ultrafilter on alpha. There are a bunch of ways to write this down. But the point is, so let's see, these should all be ultrafilters on delta 0. Okay, and but essentially U alpha is an ultrafilter on alpha. Okay, so this gives us this order on arbitrary ultrafilters on ordinals. It doesn't really matter so much that I allow them to be on different ordinals. We could always look at ultrafilters on the same ordinal because you can always just sort of move around the underlying ordinal of an ultrafilter. So if you're confused about the definition, we can just do this everywhere. We could demand that U alpha is an ultrafilter on alpha. And and U is then equal to all the A's, such that for almost all alpha, A intersect alpha is in U alpha. Okay, so however you want to set it up, these are all basically the same order. It doesn't matter. Okay, so what's the point? The theorem is, well, one, under the ultrapower axiom, the Kettinen order is a linear order of all the ultrafilters on ordinals. And the ultrapower axiom is equivalent to the linearity of the Kettinen order. So in general, you can prove in ZF, I should have said this already, that the Kettinen order is a well-founded partial order. So under UA, the Kettinen order is a well order. Which is sort of surprising because it's a definable well ordering of all the ultrafilters. Sort of, for many people, an ultrafilter, you think of an ultrafilter as a kind of a basic example of an undefinable object, like an ultrafilter on omega. But this is a very different situation. So the corollary is that under UA, every ultrafilter, every countably complete ultrafilter on an ordinal is ordinal definable. And this is sort of how you get this consequence that the Hod conjecture is true if you have a strongly compact. But another weird thing here is that this is analogous to a consequence of AD, let's say plus DC, which says that every omega 1 complete ultrafilter on an ordinal less than theta is ordinal definable. So this raised the question, does AD actually imply the ultrapower axiom, or at least the combinatorial form that the Kettinen order is linear? And this is still open, and it's a kind of important question because under AD, a lot of the analysis of sets of ordinals, so the structure of V really reduces to an analysis of ultrafilters. And that analysis is open for large enough ordinals under AD. So it's important to understand their structure, and this would be a really useful abstract fact if it could be proved. But this is still open. So this was sort of my reason for formulating the Ketenin order. Turned out that Ketenin had actually formulated it 50 years earlier. But anyway, sort of surprising, even though basically nothing is known about this question under AD, turns out that the choiceless large cardinal axioms almost imply the linearity of the Ketenin order. So they almost imply the ultrapower axiom. So this is impossible. For large cardinals compatible with choice. Nothing. So I'll show you the precise theorem in a second, but large cardinals that are compatible with the axiom of choice cannot imply anything like the linearity of the Ketenin order, because there are all these kinds of forcings you can do that totally destroy the ultrapower axiom and preserve large cardinals. But it turns out that the choiceless large cardinals are vulnerable to these forcings. They get killed by any kind of forcing like this. And part of the reason is that they imply this structure on ultrafilters. So what's the actual theorem? So if it's the same situation as before, lambda is a rank Berkeley cardinal, and kappa is rank reflecting. Then any anti-chain in the Ketenin order, so any set of Ketenin pairwise incomparable ultrafilters has injects into the kappa. So it's pretty small. And to any anti-chain in the Ketenin order on kappa complete ultrafilters. Well, we know that kappa complete ultrafilters can be well ordered. So we get a slightly better result. It has cardinality less than or equal to lambda. So this ordering on kappa complete ultrafilters is almost a well ordering. So it would be linear order if you knew that any anti-chain had size at most 1. But instead, we just get a bound on the size of the anti-chains. And so it's, since it's well-founded, you can sort of think of it as you can think of it as a pre-well order that is fairly thin. So you can think of, like, for example, all the ultrafilters of rank some ordinal Xi in the Ketenin order. So for each ordinal, we can look at all the ultrafilters of that given rank. And the fact is that each of these sets has size smaller than lambda. So literally smaller, not less than or equal to. So every level of the Ketenin order has cardinality strictly less than lambda. Of course, each level is an anti-chain. You can't compare two things of the same rank. Okay, and you can't do any better than this. Provably, because of these issues with forcing, you could force below lambda and mess up the Ketenin order, even actually on kappa complete ultrafilters. So this is the best possible theorem. It's the closest thing to the ultrapower axiom that could possibly be proved from any kind of choiceless large cardinal axiom, and it's just true. So the large cardinals are imposing this very specific structure on the kappa complete ultrafilters for kappa sufficiently large. And it's kind of surprising because it means that the large cardinals below, like this rank Berkeley cardinal, imposes a huge amount of structure on the large cardinals above lambda. So it makes it seem like, well, maybe if you add enough large cardinals in above, either you're getting a description of a very specific structure with large cardinals, which would be really interesting, or possibly you can just get a contradiction. Maybe rank Berkeley imposes so much structure on the ultrafilters that you can't have a super compact above a rank Berkeley cardinal. So something to play around with if you are interested in trying to, say, refute a Berkeley cardinal. So I'm going to show you something like a proof of this. I guess, yeah, what it comes from, what all this stuff comes from. So something like a proof of this will be very relevant to the bound on the cardinality of beta kappa of an ordinal eta less than theta epsilon plus 2 that we're going for. So the idea is, and the idea behind all these ultrapower axiom-like properties above a rank Berkeley is that as far as an elementary embedding is concerned, so if you have an elementary embedding, J from V to V, then so and J of eta is equal to eta, just some ordinal eta, and say J of the rank of some ultrafilter U in the Ketenin order is fixed, then actually J of U is equal to U. And this is very important. The set of alpha below eta such that J of alpha is equal to alpha is actually an element of U. So U concentrates on the fixed points of J. So this is key thing. So the what's going on here is this ordinal, so I should say the rank of U in the Ketenin order. So U is supposed to be an ultrafilter on eta. So it has a rank. So what this observation is saying is that according to an elementary embedding, an ultrafilter might as well be an ordinal. It's sort of totally where it's being mapped is at least the question of whether it's being fixed is totally determined by what its rank is in this order. And that's how we're gonna get everything we get. So why is this true? So let W be equal to J of U. It suffices to show that the set of all alpha less than eta such that j of alpha is equal to alpha is in W. So for the whole, to get both this and this suffices. So why then we have that A is in U, implies J of A is in W, which implies that J of A intersect the fixed points is in W. If we could show this, we'd get that. But this set is contained in A because a fixed point of J is in A if and only if it's in J of A. So this is just equal to A intersect the fixed points. So this implies that A is in W. So if we knew this much, we could conclude that U is equal to W, so which is JU. And so that would also give us that the set of fixed points is in U because it's in W and U is equal to W. But the point is, this is really the fundamental thing, and it's telling us that both U concentrates on fixed points of J and that U is equal to J of U. Is that clear? Okay, so we want to show that the fixed points belong to this ultrafilter W. The key idea is, well, assume not. Then the ordinals alpha such that J of alpha is strictly greater than alpha is in W, because W is an ultrafilter. Now let U sub alpha be equal to the set of A contained in eta such that alpha is in J of A. So notice that if J of alpha is greater than alpha, then alpha is in U alpha. Because this is alpha is in U alpha is just saying that alpha is in J of alpha. So these are equivalent. So that means that if by our assumption, the set of alpha such that, well, in other words, for W almost all alpha, alpha is an element of U alpha. Okay, but also set A is in U if and only if J of A is in W, because W is equal to J of U. And this is true if and only if the set of all alpha such that A is in U alpha is in W. Just because this is equal to J of A. Okay, but this holds if and only if, I mean, just by definition, for almost all alpha with respect to W, A is in U alpha. So this sequence of U alphas for alpha less than eta witnesses that U is strictly below W in the Ketenin order. So remember, by definition, U is below W in the Ketenin order if there exists U alpha, alpha less than eta on eta, such that A is in U if and only if for W almost all alpha, A is in U alpha. And for W almost all alpha, alpha is in U alpha. So these aren't too big. So why is this a problem? Well, now we have that U is Ketenin below W, but W is equal to J of U, and that means that the rank of W in the Ketenin order is equal to the rank of J of U, Ketenin order, which is equal to J of the rank of U. But we said that that was equal to, this is our assumption, it's fixed. So we can't have both that U is below W in the Ketenin order and that U and W have the same Ketenin rank. It's impossible. So our assumption was false. We get a contradiction. And what was our assumption? It was just that this was not in W. So that proves this little observation that if you've got an elementary embedding from V to itself, that it fixes the rank of some ultrafilter, it actually has to fix the ultrafilter. And the ultrafilter has to concentrate on fixed points. Okay, the bound on the number of ultrafilters and the semilinearity of the Ketenin order both come from this fact. So let me just tell you about how the bound works, because it actually will show you where the semilinearity of the Ketenin order comes up. And then we'll be finished. And I should mention that there's no there are no exercises, obviously. This is the end of everything. Okay, so how do you show that the cardinality of B kappa of eta is less than theta epsilon plus 2? How? Okay, not really great English, but whatever. So the idea is to look at, well, first let F be a surjection from V epsilon plus 1 onto eta. And define B to be the set of all images. Well, let's just say, yeah, whatever, images. Where I is an elementary embedding from, let's say, V eta plus omega to V eta plus omega. And so elementary. And I has F in its range. Okay. Well, for each ordinal Xi, we can define a subset B sub Xi of B by setting B sub Xi equal to all of the I image etas, such that well, I should go from V eta plus Xi plus omega to V eta plus Xi plus omega, and F should be in the range of I. And this is a little ad hoc here, but I want I to fix eta and I to fix C. Okay, so why am I looking at these things? The point is that if U is an ultrafilter on eta of rank C, then we'll always have that B sub C is contained in U. And this is just by the observation before. So the observation about J from V to V fixing any U if J of U is equal to U actually shows that if you have one of these embeddings I from V whatever eta plus C plus 1 to V eta plus C plus 1 that fixes C and eta, then I of U I of U is equal to U for U equal to C on eta, and the set of fixed points of I will be in U. And so in particular, I image eta will be in U since this contains all the fixed points. So it's just the same proof as before. Okay, so we get that this set of ranges satisfying whatever these simple properties is contained in U if U has rank C. Okay, well, what's the point of this? The fact is that for each C, there are, well, let's write it as a formula. The cardinality of the set of all U in beta kappa of eta, such that U is an extension of B sub C, is strictly less than lambda. Okay. BC can only be extended to at most lambda many ultrafilters. So what's interesting here is now we have for each C, we've got one of these sets, and we know that every ultrafilter of rank C is contained in here. So this implies in particular the semilinearity of property of the Kettinen order. It implies that the set of ultrafilters U of rank C has cardinality less than lambda because every such U does extend B sub C. Okay, so that gives us one of the theorems I stated before. Fine, but what's more interesting here is that these sets B sub C are not that big. They're all contained in this original set B. Remember what B was? It's a set of all I image etas for I from V sub eta plus omega to V eta plus omega, such that I of such that this function f is in the range of I. And this set B is the surjective image of V epsilon plus 1. So why why is B the surjective image of V epsilon plus 1? Well, if we know I restricted to V epsilon, then we can get I restricted to V epsilon plus 1, and then we can get I image of eta using F. So it's this, it all goes back to this fact from before the break, where you can compute I image eta from I restricted to V epsilon plus 1, if eta is the surjective image of V epsilon plus 1 using some parameter in the range, basically the surjection. And yeah, so that's all you need here. So you get a surjection from V epsilon plus 1 onto the set B. And this means that this sequence of B sub x's for xc less than, for xc an ordinal number, well, they're all, each one of them is, it's contained in the power set of B. So if we want to bound the number of these ultrafilters, I mean, they're not ultrafilters, they're just, so each B sub c is just a subset of B. So what we need to do is we want to bound, it's a well-orderable collection, right? Because it's indexed by ordinals. So it's not going to be true that all the B C's are different, obviously, because they're a proper class of ordinals, but these B C's are all just subsets of B. So many of them will be the same. So we want to compute how many B sub C's are there. Okay, this is what? It's a well-orderable family of subsets of B. So it's less than or equal to no, it's strictly less than the Hartog's number of the power set of B. Remember, the Hartog's number is just the least ordinal, eta. Such that eta does not inject into X. The soup of the ordinals eta. Such that eta does inject into X. However you want to write it. So we know that this well-orderable collection of subsets of B, just by definition, has cardinality less than the Hartog's number of the power set of B. So a family of B sub x's is cardinality less than the Hartog's number of the power set of this set B. But okay, we know that the B is the surjective image of V epsilon plus 1. So it follows that the power set of B actually injects into V epsilon plus 2. Right, if there's a surjection from X to Y, then there is an injection from the power set of Y into the power set of X. It's just mapping a set to its inverse image. Some kind of duality. Okay, so that means that this is less than or equal to the Hartog's number of V epsilon plus 2. If there's an injection from this into this, any ordinal that injects to here injects into here. So moral of the story is that the cardinality of beta kappa of eta is strictly less than the Hartog's number of V epsilon plus 2. And why is that? Well, B kappa eta is a well-orderable set. So cardinality arguments work out pretty nicely. And we have that beta kappa of eta can be written as the union over Xi in the ordinals of the ultrafilters that extend B sub Xi. Or really, so a better way to write it is it's a union over all the B X's of the ultrafilters U such that B Xi is contained in U. So this, the cardinality of beta kappa of eta is less than or equal to the cardinality of the collection of B X's times the soup of the cardinalities of these sets. Sorry, that's a little messy. We know each of these sets has size smaller than lambda. So that means that this is less than or equal to the cardinality of the B X's, the set of B X's times lambda, which is again less than this. Okay, so this equality follows from our bound on this family of sort of filter bases, each one of which is contained in the ultrafilters of rank C. So that's how the Ketenin order comes into play here. The Ketenin order allows us to conclude that each U extends one of the B X's, and then you show that there aren't too many sets B sub C. Okay, so what remains now is two things. There's this fact. So there's this one fact that for each Xi in a ward, the set B Xi, which was defined to be the collection of I image etas, such that I goes from V eta plus Xi plus omega to itself, and I of Xi is equal to Xi, I of eta is equal to eta, and finally, this function f was in the range of I, extends to at most lambda ultrafilters in beta kappa eta. That's the one fact that we need. And the other fact, which I'm going to omit the proof of, but it's, again, it's this another non-trivial consequence of the choiceless cardinals. Aleph V epsilon plus 2 is equal to theta epsilon plus 2. So if we know both these things, well, one of them I was just using, the other will get us the bound that we want, because, oh no, put this page in the wrong place. Yeah, so we have this inequality already. Granting the first fact, we got this. And so all we need to finish our bound on the ultrafilters is to show this equality. Okay, that's omitted. So this is it's in choiceless cardinals and the continuum problem. So it's kind of an interesting proof, but it actually there's a lot that goes into this as well, but I'm just skipping it. But the one thing to see here is it's a choiceless. It's another failure of the axiom of choice. It's saying that there's no theta epsilon plus 2 sequence of distinct subsets of v epsilon plus 2. Of v epsilon plus 1. Under AC, there is always a theta epsilon plus 2 sequence of distinct subsets of v epsilon plus 1. The way to see that is, well, what is theta epsilon plus 2? It's the supremum of all the ordinals that are the surjective image of v epsilon plus 1. So for each ordinal below theta epsilon plus 2, why not just choose a surjection from v epsilon plus 1 onto the ordinal? Okay, and now pull back the order relation on the ordinal to v epsilon plus 1. That gives you some relation on v epsilon plus 1, whose transitive collapse is the ordinal eta, whatever, up here below theta epsilon plus 2. So for each ordinal, you get some relation on v epsilon plus 1. And with the axiom of choice, you can choose a theta epsilon plus 2 sequence of distinct relations on theta epsilon plus 2. Each one will transitively collapse to it, and bigger and bigger ordinals below theta epsilon plus 2, so they're distinct. Okay, so this is another failure of AC that we need here. I'm skipping it. So I'm going to just finish by showing you this proof of this fact that I just wrote down. So the fact, just to abbreviate it again on the page that I need, is that the set of ultrafilters beta kappa of eta that extend B sub C. I'm not going to write down the definition of B sub C again. Has cardinality less than lambda, where lambda is a rank Berkeley cardinal. And so, okay, so proof, well, for ease of notation, instead of using rank Berkeley, let's just fix our J from V to V, and with kappa omega of J equal to lambda. Okay, if you wanted to use a rank Berkeley, you could just take a really big ordinal nu and fix a J from V nu to V nu with kappa omega of J equal to lambda, and it would work exactly the same. Rank Berkeley lets you fix whatever ordinals you want to fix. So we can also, let's assume that J of kappa is equal to kappa. That won't matter. J of eta is equal to eta, and J of xi is equal to xi. Okay, and suppose towards a contradiction, that the inequality does not hold. So by the well-ordered collection lemma, no, not the well-ordered collection lemma, but since since beta kappa of eta is well orderable, we can choose ultrafilters d sub alpha for alpha less than lambda, distinct and kappa complete, and extending b sub c. Right, we have a well-ordered set. We can just choose the first lambda many ultrafilters that extend b sub c in this well-ordered set. Okay, and now using the well-ordered collection lemma, we can take we can find a sequence a sub x for x in v kappa such that for any two alpha 0 and alpha 1 less than lambda, there's some a sub x in d alpha 0 minus d alpha 1. So look, the differences between any pair of these ultrafilters form non-empty sets. It's a well-ordered collection of non-empty sets of size lambda. So by the well-ordered collection lemma, we can get a not too large witness to that. Remember, kappa was rank reflecting. So in fact, using kappa completeness, we can just find our sequence of a sub alphas for alpha less than lambda, such that a sub alpha is in d alpha and not in any of the d betas for beta not equal to alpha. The way you get a alpha is you just take the intersection of all of the a sub x's for x in v kappa such that a sub x is in u alpha, d alpha. Okay, now if you're paying extremely close attention, you might notice that this intersection is actually the intersection of a v kappa index set, but I only assume that d alpha was kappa complete, which means closed under less than kappa sequences. So from the homework, if you're also paying close attention to the exercises, we know that d alpha is closed under v beta indexed intersections for beta less than kappa. And moreover, we could get that okay, so but that still doesn't quite do it, but the point is that we actually have that these filters are kappa plus complete if we want, because we could take kappa to be the least rank reflecting cardinal, which would mean that kappa has cofinality omega, and then any kappa complete ultrafilter is kappa plus complete. And all we need is a lower bound here. So we might as well be working with the least rank reflecting cardinal this whole time. Okay, so anyway, we get these A alphas. And we can even make sure that the A alphas are pairwise disjoint, if you want, just by replace A alpha with A alpha minus the union of the A betas, or beta not equal to alpha. And A alpha is in D alpha for all alpha less than lambda. Okay, so now I want to finally get a contradiction. So we have a pairwise disjoint collection A alpha of subsets of eta. And each A alpha is an element of D alpha, and each D alpha is an extension of this collection B sub C. So what the situation looks like now is the situation of the wooden proof of the Kunin consistency. We have these disjoint sets, and each of them belongs to an ultrafilter extending this fixed, well, it's not really a filter, but it's a family of sets. So it's a lot like having a pairwise disjoint collection of stationary sets. In fact, it's very much like that. I mean, okay, so what do you do? So you let B alpha for alpha less than lambda be equal to J of the A alphas. So each B alpha extends an ultrafilter. Each B alpha belongs to an ultrafilter. Some D prime alpha, where D prime alpha is equal to J of the D alphas, and D prime alpha actually extends B sub C. And this is because J of C is equal to C. So when we take J of the D alphas, we get extensions of B sub C. So in particular, since look at the set B sub kappa. Sorry, I shouldn't call these B because I have too many B's floating around. So I'll call them A prime alpha. So the contradiction I'm going to get is just like the Kunin inconsistency proof. So the set A prime sub kappa is in this ultrafilter D prime sub kappa, which extends this family B sub C. What's the problem with that? Well, J image of eta is in B sub C. This is because if you look at J and you restrict it to, well, it's in, let's call it J of B sub C. That's probably better because it's not actually clear that J of B sub C might not be equal to B sub C because we remember the definition, there was this fixed parameter F, this surjection, and now we want to move the surjection to J of F. That will possibly change B sub C. But the claim is that J image eta is in J of B sub C, because we can look at J restricted to V eta plus C plus omega, which is an elementary embedding from V eta plus C plus omega to itself. And J of eta is equal to eta, and J of C is equal to C. And this parameter, J of F, is in the range of J. So these are all the conditions that are required for putting J image eta into J of B sub C. So since J of eta is in J of B sub C, and J of B sub C is contained in D prime sub kappa, and B kappa, A kappa prime is also in D kappa prime, J image eta has to hit A prime sub kappa. So this is just, now it's just like the proof of, just like Wooden's proof of the Kuhn inconsistency theorem. So we know so J image eta, A prime sub kappa are both in the same ultrafilter, D prime sub kappa. So that means there is some ordinal, let's call it nu, in the intersection. So that means that nu has to be equal to J of nu bar, where nu bar, well, by elementarity is some ordinal that's in the union of the A sub alphas for alpha less than lambda. Why is this true? Well, nu is in the union of the A prime sub alphas for alpha less than lambda. So since J is an elementary embedding, this has to be true about nu bar with the pre-images. Okay, well, why is that a problem? So, well, say maybe nu bar is in A sub alpha 0. Fix that alpha 0. Well, that means that nu, which is equal to J of nu bar, is in J of A alpha 0, which is equal to A J of alpha 0 prime. And that's a big problem because this is supposed to be disjoint from A prime sub kappa. This is just Wooden's proof. Why are they disjoint? Well, all of the A primes are disjoint by assumption, and these kappa is not equal to J of alpha 0 because kappa is the critical point. It's not in the range of J. Okay, so that's a contradiction. So we cannot have had all these distinct ultrafilters. The D sub alphas can't have existed. So our assumption that this fact failed was false. The fact is true. And that gives us our bound on B kappa eta. Well, it gives us this first bound. So the second thing is proving the second bound. So I have 20 minutes. I'm not going to talk about it at great length, but yeah, let me just say something more about I'll talk about it for maybe 5 minutes and then stop. So, okay, the fact 2, which was that aleph of V epsilon plus 2 is equal to theta epsilon plus 2. So remember, embedded in this, one thing that you need here we need to at least know that there cannot be there is no sequence f sub xi for xi less than theta epsilon plus 2 such that each f sub xi is a surjection from v epsilon plus 1 onto xi. Right, because otherwise we could let A sub xi be equal to the pullback under F of the order relation on xi. Okay, so A sub xi would be a subset of V epsilon plus 1 times V epsilon plus 1. and each of the A sub C's would allow you to recover F sub C as the transitive collapse. And so so this would give you a theta epsilon plus 2 sequence of distinct subsets of V epsilon plus 1. So why is there no such sequence? So this is an alternate proof. An alternate proof of the Kunin inconsistency, which is new from the last 2 or 3 years. So why can there be no sequence of surjections F sub C from V epsilon plus 1 to Xi for Xi less than theta epsilon plus 2? Because it's obvious that under the axiom of choice, there is such a sequence. You just choose F sub C. Okay, so this will, I'm going to show you to finish all these talks, and a new proof of the Kunin inconsistency. So you got your J from V to V. So if there were such a sequence of F sub C's, it would have to be in the range. There would have to be one by elementarity. We can fix a sequence like this. In the range of J. Right, because if there exists a sequence with these properties, then there has to be one in J image V, which is an elementary substructure of V. Okay. So the problem is now, if this sequence is in the range of J, we can use it to define J restricted to theta epsilon plus 2 from J restricted to V epsilon plus 1. And we know that that's impossible, right? That's been the whole point of the proof today. You can never define this from parameters in V epsilon plus 2 plus this parameter, which is in the range of J. So how do you define it? Well, the point is, if you have any so we know from J restricted to, or J image V epsilon plus 1 and F sub Xi, if Xi is in the range of J, we can get you get J image Xi. Why? It's just F sub Xi applied to all the points. This is the same lemma from before the break that I've used over and over and over. Okay, but that's not enough to define J on theta epsilon plus 2, because it seems like you need to know whether Xi is in the range of J here. And that's circular, because we're trying to define what is the range of J on theta epsilon plus 2. So it's not good enough. But the point is, given any two any other, so like take a big fixed point nu with J of nu equal to nu. then given any I from V nu to V nu, I with I restricted to V epsilon plus 1 equal to J restricted to V epsilon plus 1, we know that the I image of theta epsilon plus 2 intersect J image of theta epsilon plus 2 is unbounded below theta epsilon plus 2. And so they agree on unboundedly many points C as before. And let's say that this sequence of surjections is also in the range of I. So they agree on unboundedly many C, and they both have this thing in their range, and so that means that they have to agree all the way up to theta epsilon plus 2. Because if you take any point in their common range, we know how to compute them, and the computation just uses I on V epsilon plus 1 or J on V epsilon plus 1 along with F sub C. So this tells us that J restricted theta epsilon plus 2 is equal to I restricted to theta epsilon plus 2 for any elementary embedding I from V nu to V nu, such that the sequence is in the range. And let's say I of epsilon, well, and I restricted to V epsilon plus 1 is equal to J restricted to V epsilon plus 1. Okay, it may look like I just restated the thing I just said. The point is, this is a definition of J on V epsilon plus 2, which uses only the parameter nu, which is in the range of J because it's fixed by J. The parameter F sub C, which we assumed is in the range of J. And the parameter J restricted to V epsilon plus 1. So those are the parameters of this definition. It's the unique set that's equal to any I restricted to theta epsilon plus 2, where whatever, all these things are true. I mean, okay, we use epsilon as a parameter, but that's also a fixed point of J. So this sequence of F sub C's cannot exist. Or else we contradict the theorem. Undefinability of theta epsilon plus J on theta epsilon plus 2. Okay, so that's all I want to say. The main point, I guess, of today is that there's a lot of combinatorics that just comes out of studying the definability. Properties of an elementary embedding from V to V. And there's a huge amount that's open. I mentioned a bunch of open problems yesterday, and none of it is extremely hard and technical, although I have the ability to make it seem so, maybe. Yeah, I hope that maybe one of you will solve some of these open problems. It's not that hard, and it can be fun. And thank you for listening. Thanks for attending.
Okay, thank you, Kip. It's, I mean, for these lectures, you need to get up very early, and even worse, you are sick in the last 2 days.
No.
we do appreciate you. I mean,
Well, thanks a
all of
lot.
you.
Thanks for inviting me to speak, of course.
And yeah, and I also thank Jason do a great job for TA.
Oh yeah, thank you, Jason.
Yeah, you make
I'm
all the
learning a lot of
lectures.
this myself also. So great job, Gabe.
Thank you.
And thank you everyone to be here to the last minutes. So I guess maybe we can take a picture and together to open everyone to open your camera, right? So okay. Okay, let me take the out. 1, 2, 3. Smile. Another one. Okay. Oh, do you, is someone still want to open the camera? Okay, the last one. Okay, okay. Thank you.
Thanks.
Thanks.
Bye.
Thanks.
Thanks. Bye bye. Bye bye.